Hi, welcome to the audience. This is our presentation for Engineering Mechanics BNR 17003, and we want to thank Dr. T.S. Hafizuddin bin Hassan, which is our lecturer, for giving us this golden opportunity to do our project. And the title of this project is Trust Design and Analysis for Communication Tower. Well, this is my group members, which is Jagadiswaran Morrison, and me, Jivesh Raman, and also John Uzaimi, and also Tawanisha.
Let me present our group project introduction, where communication towers play a vital role in our daily life by supporting phone, internet, and broadcasting signals. Since these towers are usually tall and exposed to environmental forces like wind and rain, they must be designed to be a strong, stable, and effective. For this project, we were tasked with designing a 15-meter tall tower with a 6-meter wide base. We selected the K-truss design because it offers a good balance of strength and material efficiency. Using engineering mechanics, we analyzed the tower using method like the method of joints and sections to calculate the internal forces. We also use AutoCAD to ensure accurate dimensions and a practical design. Our main goal was to create a safe and reliable structure that could handle real world loads while staying cost effective and effective.
Hello, my name is John Uzi, and now I will present the literature review part in our presentation. On this part, the literature review give information from past studies about the trust structure. It helps to understand how trust work, which design are better, and what force affect them. All this information supports the decision to use the K-Trust for the communication tower in this project. And now for the first topic in our literature review is the introduction to truss structure. A truss are made of straight members connected at joint and usually in triangle shape. The triangle shape helps spread load evenly and give strong support. It is commonly used in buildings, bridges, and towers because they are strong and light. Each truss member carries either tension or compression, useful for carrying heavy loads and covering wide areas without bending too much. The common types of truss include Pratt structure, Warren, and Howe. Modern software like STAAD Pro and AutoCAD help test and design truss before building them. The two main methods to analyze truss are the methods of joint and the methods of sections. These methods helps to calculate force in each member and check if structure is stable. The truss structure are chosen because they are efficient, strong, and safe materials. The four structures are shown here, which is the Pratt truss, the Warren truss, the third are the North Light truss, and the fourth are the Virendil truss. These are the example of the most common types of truss. Okay, now for the next topic for our literature review is the comparative analysis of truss design. The Pratt, Warren, and Howe are the most common truss types used in real projects. The Warren truss uses less steel and is lighter, good for medium spans, like for 10 and 14 meters. Pratt is stronger under tension and works well for longer spans. In our research also, we found out that Howe truss can resist twisting force and is cheaper for short spans, while the Warren truss has fewer parts, so it is easier and faster to build. And for earthquake or wind, Warren truss shakes less in medium size, but Pratt handles bigger tension forces better. Hollow or tube-shaped members save more materials and cost than normal angle steel. So In short, Warren is the best when saving weight and cost, but Pratt is the best for strong and tension. Howie, in the other hand, is good for cheap and simple builds. The tables here are show the findings for all of the design and for comparison. And now this is the last topic for our literature review, which is the forces on truss members and load types. Trusses carry different types of loads, which are dead load, leaf load, and environmental load. Each truss members faces either tension or compression. Wind can cause strong side pressure, especially at the top of the tower. By adding diagonal bars, we can make the structure more stable and stop it from twisting. As we can see from the figure here, when we add the bar there, the structure become more stable. And if there's no supporting bar there, it become unstable. Earthquake create shaking that can affect all parts of the truss. Top members often face the most stress, so they might need extra support. Engineers need to know where the forces go to make sure the tower is safe. So in conclusion, understanding the load and where the forces go, it helps us to design a strong and stable tower.
Okay, now theory principle. Okay, this project utilized fundamental principle of statistics and trust analysis to design a safe and efficient communication tower using a K-truss configuration. The K-truss configuration was selected from its structural efficiency as its distinctive K pattern enhanced the tower ability to resist both vertical loads and lateral forces such as wind. Core concept of this project is engineering mechanics were applied to ensure the structure remain in equilibrium, where the sum of the horizontal forces, vertical forces, and momentum equals to zero. Analytic method such as the method of joints and method of section were employed to determine internal member forces, while support reaction were calculated to understand base stability. Assumption typical in truss analysis, which is like pin to pin connected joints, joints to applied loads, and negligible member weight were made to simplify calculation without compromising accuracy. This theoretical approach ensure a structural sound and material efficiency tower design.
Hi everyone, my name is Morrison, son of K. Johnson, and my metal number is CN240319. So now we're gonna look at the mechanism of this project for the communication tower. So for this communication tower in this project we uses the K truss design where diagonal members form a K shape between the vertical bars. This design helps the tower handle the both vertical and horizontal loads. For the horizontal loads like the weight of antennas and for the horizontal loads like the wind. And the tower is 50 meters tall and with a 6 meter wide base and becomes narrower toward the top for better stability. It is built with the triangular sections stacked on top of each other, which helps keep the structure strong and balanced. All joints are assumed to be the pin connections that allow slight rotations, making the analysis easier. We use AutoCAD to draw the tower accurately and label all members for calculation. The tower stands on a pin and roller support system which allows movement and prevent extra stress from ground shifts or temperature changes. Overall, the truss works by spreading the forces through all members and transferring them safely to the ground, making the tower stable and efficient segments safely.
Hi everyone, my name is Dawanisha. I'm here to present about discussion. For the discussion, we analyze the thrust using basic static methods, the method of join and the method of sections. The results showed that horizontal member mostly had tensile and pulling forces while vertical and diagonal member had compressive or pushing forces. We also calculate the support reaction using equation. The tower uses a pin and a roller support for better stability. To make the analysis easier, we assume that joint were pins, loads act only at joints, and member weight was ignored. In real life, we will also need to consider wind, vibration, and possible buckling, but these were not included. Our result from both methods matched, and we used AutoCAD to draw the tower and check the design. Overall, the analysis shows that our truss structure is safe and balanced under the expected loads. To conclude our project, we demonstrate the effective use of engineering mechanic and static analysis in designing a truss structure for a communication tower. By applying both the method of joints and the method of sections, we accurately calculate internal force and support reactions. This calculation confirm the truss ability to carry vertical loads efficiently. The use of triangular geometry in our design provide strong structural stability, making it suitable and practical for real-world application. This project also highlight the critical importance of structure analysis not only for safety but also for material and design optimization. It allows us as students to apply theoretical knowledge to a real engineering problem. Overall, our truss design has proven to be stable and suitable for communication tower application. There's a great potential to further the design through wind load analysis and advanced modeling. Thank you.